Geology, Geology, Geology. This is Daniel Minizini, your inquisitive geologist from KPFT HD2 channel, Houston, Texas. Hello to everybody. We are at the Mini Geology radio show, the only weekly program about geology that puts in connection our beloved discipline of geology and society at large. Today we are going to talk about the geochemistry, which is a subdiscipline of geology, and we are going to have on the line the president of the Geochemical Society. The Geochemical Society was founded in 1955, and as many of the societies of geology, is a non-for-profit scientific society. In this case, the Geochemical Society has around 4,500 members in about 74 countries, and a little bit less than those, 40% they are from North America, but 30% are from Asia, and 25% from Europe. And the vision of the Geochemical Society is 3 words: explore, learn, and teach. So we're going to talk about the vision and many other things related to geochemistry with the president of the Geochemical Society, Roberta Rudnick. Roberta, she's also a professor in the Department of Earth Sciences at the University of California, Santa Barbara, and she's a member of the National Academy of Sciences. And by the way, her last award, because she has many, was the Hess Medal for the AGU in 2017, because you have to know that Roberta Rudnick, she is the world's leading authority on the composition of the continental crust and lithosphere. We are so glad to have you in here with us, Roberta. Welcome to the Mini Geology Show.
Well, thank you. It's a pleasure to be here.
Roberta, geochemistry requires the synthesis of many concepts and applications. It is a difficult discipline, and it is difficult also to teach it and to learn it. Since you are surrounded by geochemists and you are impregnated with this discipline, I would like you to describe the mind of a geochemist.
Well, you know, it's hard to say what is the mind of a geochemist, because geochemistry is an incredibly diverse discipline, and we have an incredible diversity of people practicing geochemistry. Basically, though, I view geochemistry as the application of chemical principles to the Earth and using those principles to try to understand things about how the Earth works, how it's evolved over time, the origin of natural resources. All of this falls into the purview of geochemistry, and even understanding planetary evolution and the evolution of our cosmos, which we would call cosmochemistry, is a discipline within the general field of geochemistry. So it's very, very broad, very wide-ranging, it's incredibly relevant to our society, I would say, because, you know, we're, for example, one of the major issues facing our society today is climate change, and that's because we've been burning fossil fuels and putting a lot of CO2 into the atmosphere. You know, it's a fact that the atmosphere is CO2 is rising, and it's been exponential since the Industrial Revolution. The planet is heating up. And what do we do about that? Well, one of the possibilities is that we try to sequester carbon dioxide, and that's very fundamentally a geochemical problem. So that's just an example of how geochemistry is quite relevant to our society.
And how do you get along with your colleagues that are not geochemists? Like, for instance, in this case, you should talk with the paleoclimatologist, and you certainly talk with the mineralogists and petrographers.
Well, yeah, so all of those areas overlap with geochemistry. It's hard to put, you know, draw a firm boundary. The paleoclimate is fundamentally geochemistry. How do we know that the temperature varied in the past? Well, it's geochemical data that tells us that. what were the other ones you mentioned? Petrology. Petrology is fundamentally linked to geochemistry in many ways. So there's it's in a sense it's unfortunate to try to pigeonhole science into geochemistry versus petrology versus paleoclimate. It's all part of broader scope of earth science.
Yeah, of course. And I was looking at maybe trying to understand with you, one is the moment in the history when we need this special branch of the geology to stay by itself, to create its own community, to create its own association and society, and to have its own discipline independent from the other ones.
I see. So your question is, why should it be independent?
Well, it is independent, right? So, even though we are all related to the geology, but when in history we need to have this new subdiscipline of geochemistry, which is something related with chemistry, but more oriented to the study of the Earth.
Right. Well, it's in a way it's similar to geophysics, right? So that's applying physical principles to study the Earth. And geochemistry is such a broad area, but what's nice about having it as a sort of breakaway, where we have our own geochemical conferences like the Goldschmidt conference, is that it's great to get people working in this very, very broad disciplinary area together to learn about what everybody is doing, because the same type of chemical principles could be used to study something related to, say, the solid Earth as well as the oceans and atmospheres. So I think that's why, having geochemistry as a subdiscipline within earth sciences is quite useful, and having conferences associated with geochemistry is quite useful. I know for myself, and of course I'm president of the Geochemical Society, but well before I became president, one of my favorite conferences to go to was the Goldschmidt meeting. And I think it's because the Goldschmidt conference is not really huge and overwhelming, as, for example, American Geophysical Union is an essential meeting for many of us to go to every year, but there's something like, 20 or 30,000 people that go to that every year. And it's gotten to the point where it's very difficult to really hear the science that you want to hear because it's so huge. Goldschmidt, on the other hand, we're looking at 3,000 to 4,000 people typically coming to the conference. And, of course, we have to run parallel sessions, but still there's a lot of things that you can see. It's not quite so overwhelming.
We are talking about the annual Goldschmidt conference, which is one of the most important conferences of geochemistry in the world. By the way, where does the name Goldschmidt come from for this conference?
Yeah, so it's named after Victor Maurice Goldschmidt, who was arguably one of the first geochemists. He's often considered the father of geochemistry. He was German geochemist who started working on really in the field of mineralogy, but made some fundamental observations about elements and how they behave in the Earth. For example, there's the Goldschmidt classification of the elements. So we define elements as being lithophile, meaning that they would prefer to be in the rocky portion of the planet. Siderophile elements would like to be in the core. Chalcophile elements have an affinity for sulfide. So he did some very fundamental work back at the early 20th century. Unfortunately, because he was Jewish, he had to flee Nazi Germany. He went to Norway. Didn't have a very long life. There's a really nice biography written about him by Brian Mason, who was, I think, his only PhD student that he had. Anyway, so he had such a fundamental impact, or basically generated the field of geochemistry. So we call the conference the Goldschmidt Conference, and the highest medal that the Geochemical Society awards is the Goldschmidt Medal, named in his honor.
I understand. Very interesting. The kind of the father of the geochemistry. So early 20th century. Very, very interesting. You have been participating and attending these conferences about geochemistry, especially the Goldschmidt, for a long period of time. And you're probably now organizing them yourself. How have you seen evolving the discipline of geochemistry in these last decades?
I think the first Goldschmidt conference was held, I think it was the one in Maryland, or it could have been in Pennsylvania. Anyway, it was back in the 80s, and I don't know exact number of people that were there, but it was probably in the hundreds. So it's grown exponentially in terms of the number of people that come, and the disciplinary area has grown, and there's some really large growth areas in geochemistry, namely environmental geochemistry, understanding, for example, contaminants in our environment, organic geochemistry, and, of course, paleoclimate. I think there's the whole field of atmospheric chemistry, too, which overlaps, but typically we don't get a lot of atmospheric chemists coming to the Goldschmidt conference. And there's, one of the things that we have to consider is how big we want the conference to grow, because it's kind of nice to have it in this sort of moderate size. But the field of geochemistry has just, I would say the breadth has just increased quite a lot. And there's there's whole new areas of isotope geochemistry, for example, that are coming online these days. If you look at the periodic table, about every naturally occurring element in the periodic table that has more than one isotope is now an isotope system for stable isotope studies, including uranium, which is pretty mind-blowing because there's the mass difference between, uranium-238 and 235 is pretty small, but because of the change in technology and the advent of mass spectrometers that can measure to very high precision very small changes in isotope ratios, all of these fields have opened up and are providing a lot of insight, new insights that we didn't have before. So I'd say geochemistry is a very healthy discipline. It's very active, and lots of new discoveries are being made.
You have been a protagonist of this discipline, geochemistry. And you're telling us now that it is spreading and growing and healthy, the geochemistry. What are the reasons why a discipline like geochemistry grows towards atmospheric geochemistry or environmental geochemistry or isotope geochemistry? Who are what are the factors that bring the discipline towards this or the other novel topic?
Well, there's a couple of factors, I'd say, but one of the more important ones is probably the technological developments that have occurred, the ability to measure elements and isotopes in very, very small quantities to very high precisions, or it's opening up all sorts of new scientific windows that we never sort of expected, I guess, in the past. I don't know the field of organic geochemistry well enough to speak knowledgeably about it, but my understanding is that there have been fundamental discoveries in that area, and that's why people get interested. And so technological development, allowing new insights, and then, of course, training students and having young people get interested in the topic, to study it through undergraduate, maybe go on to do graduate work, and continue on in research.
So you think, Roberta, that the trigger is the technology. So the technology is triggering the changes in the disciplines more than new ideas. So you have the technology, the new technology allows you to see differently or to see more, and then you get the ideas. It's not vice versa.
Well, I wouldn't necessarily say that. I think there's a role for both. Certainly new ideas are imperative, and and it's interesting how some discoveries can be made with data that have been around forever.
What are you thinking about?
Well, there's a couple of things I'm thinking about. To me, one of the highlights of understanding the chemistry of the most voluminous type of magmatism on Earth is mid-ocean ridge basalt. So back in the late 1980s, there was a study by Emily Klein, who was a PhD student at the time, and her advisor, Charlie Langmuir, on mid-ocean ridge basalts. And they looked at the major element composition of mid-ocean ridge basalts. And, of course, we've had major element composition for mid-ocean ridge basalts for decades at that point. And they basically harvested that data and discovered that there were trends between the chemical composition of the basalts that were erupting at a particular ridge segment and the physical properties of that ridge segment, meaning how high was it sitting or how low was it sitting relative to sea level. And they basically suggested that what we're seeing is like a fundamental difference related to the temperature of the mantle beneath. So that was using data that had been around quite a long time, but making a fundamental new discovery that really changed how people thought, I think, about how mid-ocean ridges work. And that leads me to another important phenomenon, I would say. So there's technological development, there's ideas and creativity, but there's also data. And, you know, there's just an exponential growth in the different types of data that have become available. And so one of the big challenges our community faces right now is how to harness those data, make them available to the community. So there's been development of geochemical databases. A couple of groups have done that, and those have been used many, many times over in different studies, and people continue to use them to make fundamental and novel discoveries about the Earth.
I see that. In fact, I think that you yourself, you made some of these studies using this methodology. So a recompilation, a gathering of huge data sets. The example of these extensive compilations of data is in one of your works also, on the composition of the continental crust, right?
Yes, there's that, and for that, when I was a PhD student, working with Ross Taylor in Australia, I was working on the lower continental crust, and so one of the outcomes was to try to say, well, what is the composition of the lower continental crust? And I started growing a database on high pressure or granulite facies rocks, which are rocks that have been resident in the lower crust, and use that to try to make inferences, actually coupled that with geophysical data, seismic wave velocities, and also surface heat flow data to try to place constraints on what the composition may be of this very inaccessible portion of the crust. More recently, my student Ming Tang, my former student, he's now a postdoc at Rice, used the geochemical databases to look to see how igneous rocks, certain ratios in igneous rocks can be used to trace the average composition of the upper continental crust, and had a nice paper come out in Science. But there's many examples of that type of work.
And Roberta, so now that you represent the Geochemical Society, what do you and the society do to collect, store, and make available these large data sets?
Yeah, that's a very good question. The answer is we try to help, but the big initiatives are happening through EarthCam and Kirsten Lehnert, who is at Lamont Doherty at Columbia University. She's been one of the more active people in the U.S. doing this. There have been Leslie Wyborn in Australia also has been involved in this. And so, and the funding agencies like NSF, I think they're supportive of these efforts. It's just that it's such a huge undertaking. The question is how to do it. And up until this point, I think we actually had a town hall meeting about this at the American Geophysical Union last fall that Kirsten and Leslie led. And up until this point, it's been efforts like Kirsten and her coworkers to harvest all these data that are out there in the literature. Some of them, of course, many of them are pre-electronic publishing, and so you have to actually, take the data out of published papers. But once electronic publishing came along, then those data can be available in a supplement. But that's still a huge effort to try to bring all of that data together into a single source that people can access.
So would you say that we are still in the infancy of this?
Well, we certainly are, but one of the ideas that was floated, and I think it's probably a very good idea, is to, rather than, when an author publishes geochemical data in a journal these days, what typically happens is that it goes into maybe an Excel spreadsheet that's in the online supplement. Well, that's a lot more accessible than trying to get, paper copy or a PDF that's not even searchable and get the data out of those. But the idea is that now when an author submits geochemical data, rather than, submitting their data as a supplementary file, they actually upload their data straight into the geochemical database. So it really cuts out a lot of work of having to go back after the publication and harvest those data. So I think that's probably the wave of the future, but it's not enacted yet. And I guess I'm not sure exactly what has to happen to get buy-in from the community. If this is a topic that's of interest to your listeners, you might consider talking to Kirsten, having an interview with her, because she's done a lot of work on this area.
But definitely, I'll have that talk because we are in relationship with Rice University. And by the way, we had in here also Cinti Lee for a couple of times to talk about geochemistry.
I'm very proud of Cinti. He was my first student, and he's just gone on to do phenomenal things.
And so, talking about the extensive database again, what would you do if you had like the ideal database that has all the possible data that have been produced in geochemistry? What would you use it for? Well,
I mean, the paper that I mentioned of Tang et al. In Science is an excellent example of that. So, if you don't mind, I'll just tell the story. But,
of course.
He noticed that, or we noticed that we use fine-grained sedimentary rocks like shales and wind-blown dust like loess as we go out and sample them and analyze them to get an average composition of what's at the surface of the upper continental crust. And Ming noticed that certain elemental ratios, transition element ratios, like nickel-cobalt and chromium-zinc ratios, change in igneous rocks. They change systematically with its SiO2 content. So if you go from a basalt, it's going to have a high nickel-cobalt ratio, and that nickel-cobalt ratio changes. It drops as the rock differentiates into a felsic igneous rock. And so we did our own compilation of shales, actually, and glacial diamictites that we've been working on in this realm as well. But he went to the geochemical databases for igneous rocks, and he was able to pull out all the data that exists for, nickel, cobalt, chromium, zinc, and major elements, and make these plots to show that the data follow these really nice systematic trends. And then, given that, and we assume these elements are relatively insoluble, and so we can go out to the shales and sample them, and their nickel-cobalt ratio is going to be an average of what was there being weathered at the time that shale was deposited. And so we can look at these shales through time and see how the average composition in terms of silica, in terms of magnesium, might have changed over Earth history, because we have shales that date all the way back to, the Mesoarchean, and they all the way up to today. So that's an example of how you could use database to say something very interesting about how the Earth has evolved.
And Roberta, what about the novelties, the news in these very last years about geochemistry? If you had to talk with our listeners that they are not geochemists themselves, what are the last novelties or discoveries that the geochemical community made?
Wow. That's a big question. And I don't feel like I know all the breadth of the geochemical community to really answer it very well, but I'll give you some examples that I'm familiar with. And these are just examples, because there's many really cool discoveries that have been made. But one of my favorites is from my former colleague James Farquhar, who is at the University of Maryland. And when he was a postdoc at Scripps in San Diego, working with Mark Tiemens, or maybe actually it just might be UC San Diego, because Mark is actually in the chemistry department. So he was postdocing with Mark, and he was working on sulfur isotopes. And normally people just measure 34, 32, and assume that all the different isotopes of sulfur follow mass fractionation trend related to their mass-dependent fractionation trend related to their relative masses. So people, tended to just measure two isotopes, and say, okay, we'll just assume everything's mass-dependent. Well, as a postdoc, working with Mark had discovered that there could be trends that were mass-independent, and that these were generated in the atmosphere through ultraviolet radiation reactions between sulfur species and UV radiation. And so James started working with Mark and measuring all these sulfur isotopes. And I remember, because he came to Harvard when I was on the faculty there at Harvard and gave a seminar about this. This would have been late 1990s, I think. And he told the story how, originally he started doing this work because he expected to find some very, very small but measurable non-mass-dependent fractionation, or we call it mass-independent fractionation, and that's abbreviated MIF. He was expecting to see very, very small signatures that may be related to biological activity. And so he was hoping that he could use this and look at sulfur through Earth history and maybe see biological activity, and trace back how far does life go. That's a fundamental question. What caused, why do we have life? That's another fundamental question. Of course, these are all questions that are also addressed through some geochemical studies. Anyway, so that was his goal. So he went out and he measured sulfur in all kinds of sulfur-bearing minerals, sulfides and sulfates. And you can get these going right back to, the Archean 3 billion or older. And he made a very fundamental discovery, namely that where he was looking for very small MIF signals, mass-independent fractionation, he discovered some very large signals unexpectedly. But the interesting thing about them was that they only occurred in samples that were about 2.3 to 2.4 billion years old or older. And it was like a switch was turned. So prior to 2.3, 2.4, there's this huge fractionations. And then around that time, everything went to zero. And all the sulfur in all the different sulfur minerals after that time were showing only mass-dependent fractionation, no MIF signal. What happened? What was going on? Well, what he was seeing in his data was the rise of atmospheric oxygen. And the way it works is that, as I mentioned before, ultraviolet radiation interacting with sulfur species causes this MIF signal. Well, before we had significant oxygen in the atmosphere, we had no ozone. And everyone knows, I guess, that ozone protects us from UV. There's still UV coming through, but it really filters out most of the ultraviolet radiation. But you need oxygen to have that. And so prior to there being significant oxygen in the atmosphere, there was UV radiation coming right down to the Earth's surface and creating these isotopic fractionation. And then once there was enough oxygen in the atmosphere to create the ozone shield, then it cut out and everything went to zero. Everything was mass dependent after that. So to me, that's an amazing discovery. And it's kind of typical also of how science works, at least from my experience, which is that you go into a project with an idea, you want to test something, you want to, figure out how something works, and you have a prediction, and then you discover something completely different. and all of a sudden, you're wondering, well, what the heck's going on? And you have to figure out what's going on. And so it's very well, I would say, accepted in our community that these sulfur isotope signatures are certainly reflecting the rise of atmospheric oxygen. And then Jim Casting and his postdoc Pavlov at Penn State did the calculation, well, how much oxygen do you need to cause the signal to cut out to zero? And the answer is very, very little. 20 parts per million is all you need to create enough ozone shield to remove this signature. So that's fascinating to me. And that's a perfect example of, some major discovery. We knew before James's work, there was lots of lines of evidence. Dick Holland wrote several papers. He was a professor at Harvard. He wrote a few papers, peer review papers, about all the different lines of evidence that suggests that, the atmosphere had very low oxygen prior, in the Archean, and that something happened and it changed and oxygen came up around 2.3 billion years ago. But it was never pinpointed in time like it has been since the work of on the sulfur isotopes.
You're definitely inspiring the inquisitive students that are listening to the show with these stories. And actually, I would like you to tell us more to inspire them even more, because we need to tell the students what has to be resolved yet. So my question now for you you have the overarching view of geochemistry is what still has to be resolved. There are many things, but what are close to us within our reach, within the reach of the students that they are probably studying a master or a PhD or a postdoc?
Right. Well, there's a lot of things. There's so much we don't know. There's more things we don't know than we do know. But thinking in terms of big picture, one area of very active research and discovery currently is in exoplanets. So astronomers have been able to discover, I don't know what the number is now. It's just growing exponentially. But there are many stars out there that have planetary systems. We are not unique in any way. But that begs the question, are we unique? And is there life beyond Earth? And so one of the big, exciting areas of research currently being done is in exoplanets and trying to figure out, what can we determine about those exoplanets to ask the question, may they be inhabited? Maybe there's life on them, and what would we need to see in the signature of those planets? What could we observe from Earth that would let us think that, or give us indication that there may be life beyond our planet? So that's, of course, a huge and fascinating topic. And what's really fun about this particular area of research is that the rate of discovery of exoplanets has been so high, and it used to be completely in the purview of astronomers, but cosmochemists and geochemists are getting involved, because if we can start to detect the atmospheric signature of those exoplanets, then we might have clues about whether they would support life or not.
That would be very interesting, because they would work with non-direct data. No samples, no analysis.
Yeah, exactly. That's right. Spectroscopic data, presumably. But people, I think people here on Earth have done experiments, with various types of atmospheres, and the people who study the atmosphere evolution over Earth history also have ideas about, for example, you might say oxygen, because oxygen is completely out of equilibrium with the rocks on our surface, and we can see the effects of that every day when we see, rust, iron rusting, and the rocks weathering and rusting, basically the iron's being oxidized in the rocks. So let's just say, maybe oxygen might be a signature for life, although there's lots of reasons, there's lots of debates about that, and it's not nearly as simple as that. But if you think about Earth history, and I just talked about the rise of atmospheric oxygen, well, it would really depend if we have another planet out there that has photosynthesis going on and creating oxygen, an oxygenated atmosphere. We would have to be observing it. If it's like Earth, we'd have to be observing in a particular time window in order to see it. If we were observing Earth 2.7 billion years ago, we wouldn't see oxygen in the atmosphere. So planets evolve, their atmospheres evolve, and you'd have to sort of hit it just right in order to see the evidence that there's photosynthesis going on our planet.
Roberta, what about if we come back to the Earth, we put our feet on the ground, and we ask ourselves about what are the career outlooks for the geochemists from your point of view, which you are a professor at the university, and you maybe have links with industry, maybe not so many, but you probably really care about also what the students are going to do with their lives if they cannot remain in the academia.
Oh, absolutely. And there are lots of opportunities for geochemists. I don't know, I'm not knowledgeable enough about the oil industry to talk about that, although I know you're from the oil industry, so maybe you can talk about that.
Well, definitely the organic geochemists, they lead the
well, that's
exploration.
What I was going to, yeah, exactly. So organic geochemistry in the oil industry, but then there's the whole realm of environmental geochemistry. And when I was at the University of Maryland prior to moving here, many of our graduates from that program would find jobs in environmental consulting firms. So they might be working on remediation, they might be working on detection of or tracing of contaminants. But that's a huge area that employs geochemists. The mineral industry could employ geochemists because, after all, understanding how mineral deposits form is fundamentally a geochemical problem. For example, like molybdenites. Let's say you want to find molybdenum. Well, most molybdenite is not an igneous sulfide. It's forming in hydrothermal veins, and so the molybdenum is probably being derived from granites as they crystallize. Molybdenum is an incompatible element. It gets enriched in the melt, and then when the vapor phase exsolves, then the molybdenum may partition into it, but that would depend upon what else is there in the fluid, like maybe it needs chloride or something like that to increase the partition coefficient into the fluid. So there are many examples of jobs that are out there for geochemists. including in industry of various sorts, and also in government labs. My most recent PhD student just finished her PhD. She worked on, in fact, molybdenum geochemistry and broadened it out to paleoclimatology geochemistry in the earth. Very, very broad, looking at from igneous differentiation to weathering to subduction zone processes. And she is now working at Oak Ridge National Lab. And so she's not working on molybdenum there, but I think she's supposed to be working in nuclear nonproliferation, which is, of course, a very important area. But the point is that the skills that she gained doing her PhD allowed her to find a job in a government lab that's doing really societally relevant work.
You mentioned nuclear nonproliferation, or would like to talk about nuclear power in general. So are the geochemists the professionals that they provide the source of the material for the nuclear power?
Uranium, you mean?
Yes.
Yeah. So that's obviously, we get uranium from the Earth, uranium deposits. That's a geochemical problem. Why is uranium concentrated? But the other aspect, which is equally important of finding uranium, is what to do about spent nuclear fuels, which have to be stored for 30,000 years away from people, to keep the radiation out of our soils, out of our water, etc. That's a geochemical problem.
What is the relationship in between the geochemical community and the nuclear power? And when I say nuclear power, I intend also the military nuclear power.
Right. Well, I think my former student, her name is Allison, or she goes by Al Greeny. Her job in nuclear nonproliferation is related especially to that. So there's a thing called nuclear forensics, which means that say you wanted to monitor nuclear testing in North Korea or wherever. One way to do that, of course, is from geophysical data. Seismologists may be able to detect the blasts that are made when they detonate a nuclear weapon. But the other way to do it is with looking at the nuclear, the changed products created by the nuclear detonation. And so, especially if those get out into the atmosphere or into the oceans, you could tell that somebody has detonated a nuclear weapon somewhere. That's all nuclear chemistry or nuclear geochemistry.
Is there any statement position of the geochemical community on the proliferation or non-proliferation of the nuclear power?
No, I don't believe there's any statement from certainly not from the Geochemical Society. And I don't think that American Geophysical Union has been making various policy statements and the like, but I don't believe that they either have a statement about that. I think that as humans, none of us want to see nuclear weapon proliferation. We all want to survive. We don't want a nuclear war. It could be catastrophic. So I think everybody's probably on the same page with respect to that. With respect to nuclear power, I think you're going to find divided opinion, because nuclear power is wonderful in many respects. The amount of energy that you can get from the small amount of fuel is amazing. The fundamental problem is that nuclear power generates radioactive waste, and there needs to be a way of safely storing that waste in order that we don't make people sick or kill people with radiation exposure. So the reason that nuclear power may make a comeback, and it's not clear that it's going to anytime soon, but it could, is because it doesn't generate CO2. And if we need to decrease our CO2 emissions, we need to think of, energy, alternative energies, and nuclear power is one of those. It's just that it has its own problems. Well, everything has its own problems, but, it could be quite severe. And as 3 Mile Island many years ago demonstrated, the Fukushima, problem was generated by a tsunami associated with an earthquake, but it released radiation to the oceans, to the atmosphere, and it probably, I haven't done enough reading about it, but I'm sure that it probably affected the local population. I know they had to evacuate the immediate area.
Yep, I see that you have a special relationship with the geochemist of Japan. In fact,
yes.
30% of your members, they are from Asia, and probably most of them from Japan. Is that right?
Well, I don't know how the breakdown is within Asia. I suspect we have a lot of Chinese members as well, because China is investing hugely in science and technology, and so there's many beautiful geochemistry labs that have popped up all over China. Wonderful new mass spectrometers and clean labs. So I probably, if I had to guess, I'd guess it might be the Asian contingent of the Geochemical Society would probably be about half and half, but I don't know for sure.
And Roberta, beyond the goal of disseminating and data informing the community, what are the overarching goals of the Geochemical Society?
I think some important goals are helping geochemists in developing countries, in Africa, in South America, other parts of the world, Southeast Asia. There are geochemists in those parts of the world, and it can be very difficult to do research because of funding situations. So we really would like to bring the whole world into the broader geochemistry community, really promote geochemistry in those regions, as well as the more typical strongholds, which is North America, Europe, and China, Japan. So that's one. And then the other important goal is developing the next generation of scientists. So we have been trying to raise funds to support attendance at the conference by young scientists, particularly from low-income countries. We've had a grants program from them for such students for a few years now. Also, within developed countries and within America, broadening the diversity, the representation of diverse populations within our science, because we know there's scientific studies that show us that having a diversity of people working on a problem tends to lead to greater breakthroughs and understanding than just having one segment of the population participating.
I appreciate these three main goals that you mentioned. I'd like to talk one by one about them. So, because I know that the first one, which you mentioned, help the underdeveloped countries. I know that the Geochemical Society, together with the European Association of Geochemistry, have outreach activities in underrepresented regions of the world. And would you like to talk about that?
Absolutely. So we've been trying to provide outreach to those areas. We've jointly sponsored lectures to go to, for example, sub-Saharan Africa, and there's a new discussions about creating a grants program. So the Geochemical Society has had what we call a meeting assistance program for many years, and people can apply. If you're running a meeting that has geochemistry as part of it, you can apply for a small grant from the Geochemical Society to help run that meeting. But we're going to try to broaden that to allow maybe develop a program. It's not yet decided, but there's basically brainstorming that's going on, but perhaps develop a program that would allow a person from one of these low-income countries to travel to a geochemical lab, well-established lab somewhere else in the world to undertake analyses. So that would be one possibility. I spent part of my sabbatical in Tanzania in University of Dar es Salaam and actually helped teach the geochemistry course there with my colleague Shukrani Manya, who was teaching the geochemistry course. That was a fantastic experience. It was a large class, 30 students, something like that. Most of the students who graduate with a geology degree from the University of Dar es Salaam end up working in the minerals industry because there's very active exploration going on. But I was really hoping that I could, tell those students about the possibility of going on to do graduate work in the U.S. or in Europe. And it's a big hurdle, though, because they have to take the TOEFL test of English as a foreign language, and they have to take the graduate record exam. And those cost over $100 each, maybe more now.
205 precisely.
Yeah, and so that's prohibitively expensive if you're living in, Tanzania. There's just no way. So I wanted to try to, help pay for any of the good students in that class who wanted to try to, go off and do graduate work in other country. I wanted to try to assist them to do that. It eventuated that none of them in that particular class went on, but I think they didn't know that it was even a possibility. It hadn't even crossed their mind that it would be a possibility because of the prohibitively expensive exams, and also, how do you go about applying to a graduate program somewhere else? So that's the sort of thing that the Geochemical Society could help with.
There are the other two topics that you mentioned that I don't want to forget about. One, training the next generation, and second, diversity. First, training the next generation. So one of your most important roles is teaching and training you personally, even though also the Geochemical Society, as you mentioned, training the next generation of students, but next generation of professors. So what are the core values you pass on to them? So not necessarily the technique, the method, but what are the values that you pass on to them?
Well, obviously one of the most important things is honesty. That if you publish something, you need to be able to stand behind it. Your data should be of impeccable quality. And also, I think as important is having a collaborative spirit. That is, that rather than feeling like you're in competition with somebody, how about working together? Because personally, I find that you can make a lot better headway doing that than being in competition. It always drives me crazy when, and there's many examples of this, when, one lab will report some data, and then the next lab will report some data that's in conflict with the first lab's data, and then the question is, well, why? And what's going on? Well, you can get to the bottom of that. You have to share samples. You have to be willing to, to do cross-lab comparisons, but not everybody is willing to do that, and I think it's a shame. So I like to instill in my students that you shouldn't be afraid of, everybody should be looking for facts and the reality, defining the reality, and if you happen to be wrong about something, that's okay, because you're gaining information, you're making great strides if you figure out you're wrong. So that's something that's not formally taught, but I try to instill that in my students.
So let's wrap up in here then, because I want to mention also the other topic that you brought in, which is the diversity. And I would like to ask you how geology is changing now that there are more women. Among the diversities, women doesn't fall into that bucket, but it's very important for science and for geology.
Yes.
This change. What are the challenges for women that they face in geology now?
Well, it's amazing. I've been in the business, I don't want to think about how many decades, and the number of women who are full professors, for example, is still very low. And when I was an undergrad, I was pretty sure that the proportion of men to women in my class was about 50-50. And so what's happening? This has always been a problem, the so-called leaky pipeline. But I think that there's been studies that have shown that that this thing called implicit bias, which means that it's a bias everybody holds. I have it, you have it, everybody, because you're brought up in a certain culture and you associate certain things with different genders, and implicit bias can really play a role. People are not meaning to be discriminatory, but through their actions they end up being unconsciously. And I think just recognizing that exists is a really important step forward. But there's many issues. Providing adequate childcare, for example, for women in the workforce in general, is still a struggle to find good childcare in many cases, affordable, especially if you're a graduate student. I mean, having a child while you're a graduate student is the ultimate challenge, I think. So it's that sort of thing that we can start to address.
Thank you, Roberta. Roberta is the president of the Geochemical Society, Roberta Rudnick. Thank you very much for being with us at Mini Geology, the radio show, and you can listen to your own interview in minigeology.com, which is a YouTube channel. Thank you very much.
Okay.
Roberta.
Thank you.
Yes.
It was a pleasure.